Polynomials. So you've been working with polynomials in grade 10 when you did linear functions. You worked with polynomials in 20 when you did quadratic functions. And now we're saying those two things that you learned in 10 and 11 are really the basis for now these generalizations we're going to make for all polynomial functions. So biggest thing we have to understand is what's a polynomial function? Because it has specific characteristics. So polynomial functions are any function whose equation can be written in this form. And this looks really complicated. All that really means is I have some sort of a coefficient. I have a variable to an exponent. Here's where it's important. The exponent must be a whole number. Now, quick review of whole numbers. Whole numbers are 0, 1, 2, 3, 4, 5, blah, 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 blah. So I can't have negative exponents, and I can't have fractional exponents when we're dealing with polynomials. X has to be a variable. It's got to have a variable to an exponent. And the coefficients are real numbers. So in this chapter, we're going to be dealing with integrals, but the coefficient could be root 2, but we're not going to deal with wacky stuff like that, but it could be. So understanding those definitions of polynomial functions, let's make sure we can identify which ones are polynomials. Is A polynomial function? Well, do I have a coefficient, a variable to an exponent, where the exponent is a whole number? No, my exponent is the variable in this case, and that's not a polynomial function. This is actually an exponential function. So no, the exponent is not a whole number. Or you could write, no, the exponent is a variable. Both of those are valid reasons why that is not a polynomial function. B, is this a polynomial function? Well, I take a look. I've got nice coefficients. Base to an exponent is my base in x. Yes? Are my exponents whole numbers? Yes. That is a polynomial function. That's what we're looking at. Base with exponent, the base is a variable, exponent is whole number. Is C a polynomial function? No, why not? Well, there's the problem. -1 is not a whole number. So no, -1 is not an element of whole numbers. I'm getting mathy on you because that's the way I do it. Y is equal to 4. Is that a polynomial function? Now I want you to really, really think about this definition. Do I have a variable to an exponent that's a whole number? Well, I don't see the variable, but what do I know about whole numbers? The very first whole number is 0. And anything to an exponent of 0 is 1. So do I ever need to write x to the 0? Or mathematically, is that a redundant statement? So this is because we don't see x to the 0, even though technically it's there. So math has a whole bunch of these implied things that we never really, we just do. Like, that x, that has an exponent of 1. Well, we don't write it. We just know it's there. Well, that has an x to the 0. We don't write it, but we have to acknowledge it's there, making this a polynomial function. So all these little implied things in math that happen. E, is that a polynomial function? Well, I need to look, does it have a variable with an exponent that's a whole number? Well, I've got the x, but when I finish working through this, that is going to be an exponent of 3/2. Remember 10c? 3/2 will be that exponent. So no, x has an exponent of 3/2 because that radical is the denominator of the exponent. So we're looking for that x to a whole number. And sometimes it's implied. So we've got to acknowledge that. Okay, way back in 10C, one of those things that we taught you, then we talk about for like 5 seconds, and then we move on from and expect you to remember into 30-1 is this. The degree of the equation is basically the highest exponent you see. So we do that when we do chapter 3 and 10C, and we never talk about it again. But degree 1 is a linear function. You worked in grade 10 with linear functions, remember? An example is something simple like y is equal to x plus 7. That has an exponent of 1 implied, and that is the highest degree because, as we've said, technically that has an x to the 0 there that we don't talk about. But 1 is the highest exponent. Quadratics are degree 2. You got very familiar with quadratics in 20, whichever 20 you took. And again, when I look at all of my x's, the highest degree is 2. Cubic function. Well, cubic is degree 3, so let's do 8x cubed minus 2x. All I'm looking at are the exponents on the x. Highest one's 3, it's cubic. Quartics will have a highest degree of 4. And I mean, it really doesn't matter how many terms I've got in that particular equation. I could stop with 1. There's nothing wrong with that. Quintic is my degree 5, so let's make something like, I don't know, 7x to the 5 plus 6x squared minus 2x plus 8. All I'm looking at is the exponent on the x, highest one, will define the function, and that is going to be what gives us our characteristics. Leading coefficient. So this is the coefficient in front of the highest degree term. This leading coefficient is going to give us a characteristic of the graph. So for example, the leading coefficient in my first example was 1. That's the leading coefficient. Now in 10C, you learned that was the slope. And because the slope was positive, you learned which direction it was going, right? That was an increasing line. If it was a negative, it would be a decreasing line, correct? Remember that from way back when? Okay. Degree 2, leading coefficient, in our case, was 2. Well, that 2 told you something. Because that was a positive 2, that was a parabola that opened up, correct? If that 2 was negative, it would have been a parabola that opened down. So that leading coefficient is actually going to give us some characteristics of these graphs. I knew it was a parabola because it was a quadratic, and I already know which direction the opening is. So by just looking at that equation, I already have some information about what it's going to look like. We're going to extrapolate from that as we go. Leading coefficient here was 8. Does that make sense? 6, 7. So that very first term that we see, that leading coefficient, that's going to become really important and give us something about what that graph is going to look like. Constant term. The constant term is important. It is the term independent of x. So for example, our 7 was a constant. It didn't have an x because we would never write x to the 0. It's negative 5 in my quadratic. It's 0 in my cubic. So it's technically there. It's got a constant of 0, a 0 here, and an 8 here. Now typically, our constant term we've been using to show the y-intercept when we were in standard form or in general form. So that, again, that constant does give us a characteristic that is going to become important. All right, so let's take a look at some polynomial functions. So we're going to pull out our graphing calculators. Well, you are. I'm not a big fan of the graphing calculator. But we can sketch these. So if I have a degree 0, we call this a constant function because it merely contains the constant of the equation. It doesn't change either. So if I have y is equal to 6, when you guys type y is equal to 6 into your graphing calculator and you graph it, well, you learned in 10C, a y equals line is a horizontal line. So this is simply going to go through 6, and is going to be a horizontal line. And it doesn't change, it's constant, it's always 6. So y is equal to 2, again, this is a horizontal line constantly at a y value of 2. We did that in 10C. All right. What would the graph look like if the leading coefficient, the a value, was negative? Well, if I had something like y is equal to negative 2, it would just merely mean that my horizontal line is below the x-axis. So this one's kind of self-explanatory. So I would say the horizontal line is below the x-axis. That question's kind of redundant in this particular scenario, but that leading coefficient is going to be something very important and very defining. Constants, all good? All right, linear, throw you back into 10C. 10C, degree 1, we focused on lines for 3 chapters, linear functions. You learned y equals mx plus b will give me the slope and the y-intercept. So when I look at y is equal to x, yes, you can use your graphing calculator, but really, should you by now, considering we worked on that in chapter 1, know what that line is? Y-intercept is 0, slope of 1. Do I need arrows on the end, by the way? Please? They will mark, like again, you're not writing the diploma, guys, but they would be marked wrong if you did not have arrows. All right, y is equal to 2/3 x minus 2. When I look at that again, yes, go for it. Type it in your graphing calculator. However, I see this as linear because it's degree 1, has a y-intercept at negative 2, and a slope of 2/3. I'm trying to refresh your grade 10. So I would start down here at negative 2. I would go up 2 over 3, and I end up having an x-intercept at 3. It is a positive slope. Therefore, there we go. Grade 10 could have been a long time ago. All good? All right. So, the leading coefficient, in this particular case, the slope, would be different if it was negative. So if my leading coefficient was negative, if my slope was negative, what effect does that have on the graph? Instead of an increasing line, it's a decreasing line. The line would decrease. We know that. We're just refreshing these generalizations we're going to make. All right, then you graduated from grade 10 and you went into grade 11 or 20-1, and we did our quadratic functions. So our quadratic functions are the shape of a parabola. So again, as soon as I see that highest degree term is x squared, I know the shape. We know that this is just a lovely basic parabola with a vertex at 0, 0. Now again, feel free to pull out your graphing calculators. As soon as I see sketch, I get a little loosey-goosey with what I'm doing. I look at that and I say, okay, I know this is a quadratic because the highest degree is 2. I know it opens up, and I know I have a y-intercept at negative 2. So that's kind of my thought process when I glance at a function. So straight away, I know the shape and I know the y-intercept. If we didn't have our graphing calculators and we wanted to find the x-intercepts, could we? It's the factored form. Remember that? We saw that a little bit again. So we could factor that, and we could say, okay, what is this going to factor into? X minus, what two numbers multiply to negative 2 and add to negative 3? That doesn't happen, does it? So this is going to be ugly, and because it's ugly, I'm not going to care too much about it. We could find the vertex form if you guys really wanted to. Anybody want to find the vertex form? No? So the most that I would want to use for my graphing calculator, and I will pull it up even though I don't like it, x squared minus 3x minus 2 I would just want to see is the vertex to the left of my x-intercept or sorry, my y-intercept or to the right. So based on that, I can quickly say, here's what it looks like approximately. And for a sketch, for our purposes, that's fine. Okay, again, because of that squared, I know it's quadratic. Because of that 2, I know it opens up and it's a parabola. This form, I can tell the vertex is going to be at -3, 1. And because this is the vertex and it opens up, I'm pretty aware there's going to be no x-intercepts. So the only other characteristic that I would need to have is the y-intercept. Make x 0. 3 squared is 9, times 2 is 18, plus 1 is 19. And there's my lovely sketch. And truly for sketches, that's all we need. Doesn't have to be perfect. All right. Quick review of 20-1, but we've been kind of reviewing this as we go. So what would change if my leading coefficient was negative? Well, instead of a parabola opening up, we would have a parabola opening down. That's all it tells us. So the parabola would open downwards. So this is the information that we're going to use to actually start to make some nice generalizations. So we gave you some serious foundation in 10 and 20, and now we're going to use that to extrapolate in 30. So degree 3, here we go. Now we're new. Cubic function. I don't expect you guys to know what these look like. So now, yeah, we really should be using our graphing calculator to investigate what's going on. So let's take a look at what y is equal to x cubed looks like. All right, x to the power of 3. Something new, we haven't seen that before. Okay, totally different. So we go, that's interesting. It goes down, it dipsy doodles, and it comes up. You'll get better at that dipsy doodle the more you do it. Cool. Okay. No pattern yet. So let's graph another one and see what it looks like. So now we've got this 3. Let's clear that out. 3x to the power of 3. Oh, and I've forgotten what it is already. Minus 7x. Okay, what does this look like? Oh, wow, that's a lot different. Okay, so it goes up, down, up. The only thing I'm going to consider really important is it passes through the origin. For now, that's going to be good enough. So it goes up, down, up. Okay, well, those look really different. Do you see anything in common? You know, as we start to evaluate patterns, what's going on? Well, let's get another one so that we can see what's going on. Here we've got x minus 7, x plus 1, x plus 4. Let's see what that looks like. And I just said it and I don't remember. I think it was x minus 7, x plus 1, x plus 4. Okay, well, first thing I noticed, okay, this one's in factored form, right? Do you notice that this is factored, right? Okay. Let's graph. Oh, wow. Okay, that's totally weird. It even goes off the chart, right? Okay, so if I'm doing a sketch, if my x and y intercepts are nice, I'll use them. Does this have nice x intercepts? What are my x intercepts? -4, -1, and 7. Does that relate to the factors at all? Are you noticing a connection between what you learned about the factored form of a quadratic, and now we're kind of using the factors give us x-intercepts? Okay, I couldn't see what the y-intercept was, so if I really wanted to, I could change this, go to a minimum. I should know what that is actually off the top of my head, and I don't because I'm not paying close enough attention. I apologize. So I could graph it, trace 0, find my y-intercept at -28. As you can see, I don't like graphing calculators. I would have just put 0 in. That's really what I would have done. -7 times 1 times 4 is -28. And we say, okay, this goes up, down, up. So the first connection I made is the factored form gave me my x-intercepts. So the factored form does the same thing it did when it was a quadratic. So the factored form is very useful for graphing, correct? So that's going to be an interesting challenge. Do you know it? And notice any other patterns? It always started in quadrant 3 and ended in quadrant 1. Started in quadrant 3, ended in quadrant 1. My linear functions started in quadrant 3, ended in quadrant 1. Started in quadrant 3, ended in quadrant 1. So does my cubic behave a little bit like my linear? A little bit. So the line would decrease was our answer here, but let's think in terms of quadrants. If I had a negative leading coefficient, it would start in quadrant 2 and end in quadrant 4, right? So my prediction is that if I have a negative leading coefficient, maybe it's going to flip this around. Well, before we state that, let's really look at it. Let's take our basic parabola, our basic cubic, and make it negative and see what happens. Is our prediction correct? I'll go to, what did I do? I did negative instead of that. Was our prediction correct? So that negative, if you want to think about it, it did that reflection, or we can think about it, it behaved the same way a line does. So what we learned about lines, about positive slope and negative slope, actually works. So it would start in quadrant 2 and end in quadrant 4. So in the example we used was this one. So again, I could think of that as a reflection about the x, or I could say this is like a positive slope and this one's like a negative slope to connect it into the lines. Whichever way you want to think about it. Does that make sense? So I'm tying it into a line. I'm showing you the connection. Okay, degree 4. This is quartic. All right. New base graph. Let's take a look. So if I have x to the power of 4, what does that look like? It looks like a parabola, doesn't it? Now, it's a little bit different than the parabola. Do you see how that's a little bit flatter? So it's like a parabola, but it's not perfectly a parabola. It has the same behavior, but it's a little bit flatter. So do you think this is going to behave a little bit the same way as a parabola by any chance? Well, it looks like a parabola opening up right now. So let's take a look. How about we graph this next one? X to the x, so 3, 2, 1, -8. I have to remember it as I go. Okay, so we had x to the power of 4. Was it plus or minus? Help me out, guys. Plus 3x to the power of 3, plus or minus? 2x squared plus x, then it did -8, correct? Yes, thank you for your help. Okay, so degree 4, positive leading coefficient. Okay, that is funky looking. Okay, that's really odd, but that's okay. Are my x-intercepts nice? Not really, so I'm not going to worry too much about those right now. But you know what? I'm going to go grab the y-intercept just to give myself something. Now, I knew what that was because the constant of the equation is the y-intercept. So, but this has a weird dipsy doodly thingy jiggy. So, -8, it went down, it dipsy doodled, and it came up. But it started in quadrant 2 and ended in quadrant 1. Started in quadrant 2, ended in quadrant 1. Now, Deep breath. Let's see if you can do this next one without a graphing calculator, considering what we've already been talking about. If I give you the factored form, I am giving you the x-intercepts, correct? So this gives me an x-intercept at 0. My next factor gives me an x-intercept at -2. This next factor gives me an x-intercept at +2. And then I have that last one gives me an x-intercept at 3. I can find the y-intercept, which is really easy because I have an x-intercept at 0, so that's already there. So if I'm going to sketch this, how do I know where I'm going to start? What quadrant am I going to start? Well, it behaves like a parabola, right? So it would start here. Oh, that's terrible. I'm on the wrong side. It would start here. It would go up, down, up, and make kind of like a W. There's our prediction. Did every step we took make logical sense? So now we're using the information given to us. Well, let's graph it just to make sure that we're not being completely ridiculous, even though you guys are like, well, you're the teacher, you should really know. I know. We're investigating though, because it's so much fun. Well, it's not perfect. One went farther down, but did we essentially get it right? So just so you know, that low point, that high point, and that low point, for 30-1, you would just find those on your graphing calculator to make a good to make a good sketch. That is still a maximum, that is still a minimum in your trace function. Calculus, we will find where those are using a different method. Okay, but right now, you would just use your graphing calculator. There's no algebraic requirement for it. That comes later. So, behaves like a parabola, behaves like a parabola, behaves like a parabola. So if my leading coefficient is negative, what's it going to do? It's going to behave like a parabola, correct? So, what would the graph look like if the leading coefficient is negative? It would start in quadrant 3 and end in quadrant 4. So my statements that I'm writing, do you see how I'm changing it from behave like a parabola to being very specific about where it starts and where it ends? So now we're using quadrants to be defining the characteristics. How's it going? So far, so good? You seeing the links that we made? Why it's so important to get everything in all the other courses? All right, degree 5, our quintic functions. Well, totally new again. Let's take a look at what this base graph looks like. So clear that out, all that work. X to the power of 5, we graph it. Well, it looks almost exactly like a degree 3, right? A little flatter in that middle, but essentially, this is going to behave kind of like my degree 3. So, positive leading coefficient, it's going to start in quadrant 3, end in quadrant 1. Well, yuck. I know this is a degree 5, so it's going to start in quadrant 3, end in quadrant 1. And remember, I also know the y-intercept is going to be up there at 3. So when I just look at that equation, I can now say it's going to start here and end here. And in that form, I have a y-intercept. So that's kind of what we can pull out of the equation. So when we glance at things, we can pull out what's going on. Now, to tell you the truth, I got no other idea what's happening. But I know it starts here, and I know it ends here. So that's good. That's my personal little notation that I use when I'm like, it's odd and positive, it does this. All right. There's no way I'm going to remember that. Okay, you guys can call it out to me. You're pretty good. So, x to the power of 5. Guys, can you help me out? What's next? Negative 4x to the power of 4. So plus 2x cubed, 2x squared plus 3. That good? Awesome. We hit graph and we're like, okay, that's really funky. And don't worry, we'll get to the funky. But it started in quadrant 3, ended in quadrant 1. It had a lovely y-intercept at 3 that I predicted. And these aren't pretty. And I'm not going to worry too much about the high points and the low points right now. That's not the point. But this goes like that, something like that. And that's all that matters at the moment. All right, little predictive power here. Factored form, love factored form. It's awesome. Factored form gives me x-intercepts. So right away, I already know this is going to have an x-intercept at 0, at -2, at -1, at 2, and at 3. We love the factored form. The fact that the leading coefficient was positive meant I was going to start in quadrant 3 and end in quadrant 1. So you see how we're now using all of that predictive power. Because I have an x-intercept at 0, I will have a y-intercept at 0. So the graph is going to look something like this. And these points I would go and find on my graphing calculator. But to tell you the truth, at this moment, that doesn't matter so much. I'm not trying to be that precise. So let's see how our predictive powers were. X, here we go. X plus 2, x plus 1, x minus 2, x minus 3. I think I got it. Yeah, good enough. Now, did anybody notice anything as they drew this one? It's a degree 5, and I went 1, 2, 3, 4, 5 directions. If we go up a little bit, this is degree 4. I went in 1, 2, 3, 4 directions. Something weird happened here because I only went in 2 directions. And that dipsy doodle created another little problem. But shapes are going to start to be able to be predicted as well. But we're going to need more information. I'm just pointing some stuff out. So if our leading coefficient was negative, we can think of that as a reflection across the x-axis. So we can tell that this would look like that if it was negative. But I could also say, if this acted like a positive sloped line, this will act like a negative sloped line. So what would the graph look like? It would start in quadrant 2 and end in quadrant 4. So I can start to look at a graph, determine where it starts and it ends based on its degree and its leading coefficient. I might be able to pull out the x-intercepts. I might be able to pull out the y-intercepts. So you see, by just glancing at the equations, we're going to start to be able to see the graphs. So that's where we're leading to, that predictive power. Okay, let's summarize. Linear is degree 1. We are generalizing, and the start and the end behavior depends on the leading coefficient. So I would say if A is greater than 1, okay, it's behaving like a line, which means it's going to start in quadrant 3 and end in quadrant 1. Start and end behavior. However, if the leading coefficient is less than, oh, sorry, that shouldn't be 1, guys. That should be 0. My apologies. I was thinking ahead of myself. However, if the A value is negative, it started in quadrant 2 and ended in quadrant 4. Reminder of the quadrants. So our line either went from 1 to 3 our line went from 2 to 4. All right, domain. Well, if it's a line, the domain is XER. There was no restrictions on it. Because it was a line, the range was also XER. And a line always had one x-intercept, always. All right, our quadratics, which are degree 2. If I had a positive leading coefficient, it started in quadrant 2 and ended in quadrant 1. If I had a negative leading coefficient, it opened down, which means it started in quadrant 3 and ended in quadrant 4. So we're getting away from the opening up, opening down. We now have to define it with quadrants. So that's kind of the step that we're taking. The domain. Parabolas had an unrestricted domain. However, the range, this had a high point or a low point, correct? So it was either going to be up from the Q value or below the Q value. And I'm using Q from that vertex form of the parabola. So my range would be restricted. How many x-intercepts did a parabola have? Did it always have 2? Did it always have 1? Did it always have 0? So we have to state it could have 2, 1, or 0, depending on its position. Okay, so there's the familiar stuff. Then we generalize. So now when we go to our cubic, which is degree 3, it behaves like a line. So it is going to have the same start and end behavior. It behaves like a line, which means if A is positive, I start in quadrant 3 and end in quadrant 1. If my leading coefficient is negative, I start in quadrant 2 and I end in quadrant 4, just like a negative line. Does the same thing. Its domain is unrestricted. Okay. Its range, it behaves like a line, right? It goes like this somehow. So its range behaves like a line being unrestricted. Now, how many intercepts does it have? Well, I can think of it that I'm going in 3 different directions. So could it have 3? Absolutely. Okay. Could it have 2? Well, I could go like that, couldn't I? Did I go in 3 different directions? That kind of makes sense. So it could have 2. Could it have 1? Well, remember that first graph that we did with the cubic where it just went like that? So it can have 1. Can it have 0? No. It's got to cross through somehow, some way to get from quadrant 3 to quadrant 1. So it can have 3, 2, or 1, but it's going to have 1 at least. Okay, quartic. What did quartics behave like? Parabolas. So it is going to repeat the start and end behavior. It's going to be like a parabola opening up if A is positive, and it's going to behave like a parabola opening down if it's negative. Domain. Well, it behaves like a parabola, so it has an unrestricted domain, but it's also going to behave like a parabola that it is going to have a high point or it's going to have a low point. So I need to go away from the Q. So I am either going to say it has a minimum to infinity, or it goes up to a maximum from negative infinity. So now we're going to start to talk in terms of maxes and mins. So I'm just kind of progressing the generalization. All right. behaves like a parabola. How many intercepts can this have? Can this have 4 intercepts? We saw that one, remember? Could it have 3? Well, 1, 2, what if I touched? Would that be 3? So it can have 3. Could it have 2? Well, if I touched for it to only happen once, could I go touch, touch? Would that work? That still went in 4 different directions, so it can have 2. Could it have 1? Well, if I cross, does it have to come back down? Like if I start down here, if it's going to end down here, does it have to come back? Yeah, so if I cross it once, am I going to have to cross it again? Sure, but what did we see for 1? Do I have to cross it? No, so what could I do instead? Touch, and then I could actually have another little thing. So I can go up and touch, but then I don't have to cross it again. So it's got this little weird thing. Can this one have 0? Well, I just kind of saw that. I could go up and touch and then not come down. Could I have taken that graph that I just drew and moved it, transformed it down, and then it would have 0? So you see how it behaves like the quadratic. I can have up to 2 all the way down to 0. I can have up to 4 all the way down to 0 because it's even. But these ones, my odds, I can't have 0. So there's the pattern that we're trying to develop. So quintic. Quintic, degree 5, behaves like a line. So it is going either from 3 to 1, or it is going from 2 to 4. It behaves like a line. Unrestricted domain, unrestricted range. Now, without doing all the drawing this time, if it behaves like a line, what's the maximum number of x-intercepts it can have? 5. What's the minimum number of x-intercepts it can have? 1, because it behaves like a line. So it can have 5, 4, 3, 2, or 1. So now we got into prediction as opposed to investigation. We found a pattern, and then we used it. So that's what math is, finding a pattern, creating a rule, using it. Okay, so state the following functions, degrees and leading coefficients. Starts in 3, ends in 4. So first thing I know is that the leading coefficient is going to be negative. To me, that looks like a parabola opening down, right? Now, their degree. Well, I know this has to be even, so let's count the directions. 1, 2, 3, 4. So does that make sense that that would be a degree 4 with a negative leading coefficient? Okay, this is still general. For those of you who are repeating, you know that we go further than this in a bit, but for now, we're going to count the directions. I look at this end behavior, and I say that's like a line. So my leading coefficient is positive because it's like a line going up. Count the directions for the degree. 1, 2, 3. So this is of degree 3. So can you do the last 2? I mean, I can do them really quick. How about you guys do them, and then we see if you understand or if we have something to clarify. How'd we do? All good? Making sense? So now you can kind of look at an equation and know where it starts and ends. Okay, you've also got some sort of idea of the shape. All right, so cubic function is defined by the function x cubed minus 12x plus 10. Use your graphing no, you don't need a graphing calculator. What's the y-intercept? 10. It's the constant. Okay, y-intercept is the constant. Make x equal to 0. That should be second nature. X-intercepts. You can't do that algebraically yet. It's coming. But now, yeah, let's go use our graphing calculator to determine that. Okay, x to the power of 3 minus 12x plus 10. Okay, I'm going to go get my x-intercepts because that looks like fun. Second function trace 0. If I want to find this one, I know -6 is to the left and -1 is to the right. So I got -3.82305. Now again, I do that differently than some teachers. I don't like pressing down on the arrows on the smartboard. You can just pick a number to the left of the intercept, pick a number to the right, and you can just manually enter those if you want. So that's what I do. Okay, -3.8, blah, blah, blah. So 0.82, and I'm just going to leave it at that because my memory isn't that good this morning. All right, I'm going to go get another one. Second function trace 0. Again, for this intercept, it looks like 1, so I know 0 is to the left, 2 is to the right, so I go 0, enter, 2, enter, enter, because I am lazy. So I get 0.89. I'm going to do 2 decimal places. For my last one, it looks like it's 3, which to me tells me that 2 is to the left of it, 5 is to the right of it. 0.293. Sorry, 2.93. All right, so now we've got 10. We've got our -3.82. We've got our 0.89, and we've got our 2.93. Looking good. Positive leading coefficient for degree 3 is like a line. So that's my little technique. I put little arrows where I start and where I end. Looking at the equation, I can see my domain is XER, my range is YER. You'll hear me say unrestricted, which just basically means XER and YER. And then we do a cute little sketch of the graph that can really look like anything. If I wanted to get intense, which I don't in 30-1, but for those of you who like to do things very particularly, I could go and find that minimum value here, and I could say it's between 0 and 3. And I could actually find my maximums and minimums and give a really beautiful sketch. Not required at this level. Don't worry, we'll do it in calculus, okay? I'll get you, don't worry about it. So that's good enough for 30-1. Pretty easy? Pretty simple. Okay, so why don't you guys do this one by yourself? Start to finish. So the additional step there was you needed to go and find that minimum value to state the range. So that was that little extra thing in this question and the other question. Could you go and get that minimum value for your range? Did anybody have trouble doing a minimum in their calculators? We're good? Fantastic. You'll notice that my sketches I purposely make very sketchy. Okay? 30-1 is still very good enough. All I do is indicate the relevant points. And unless they ask for it specifically, label your local maximums and minimums, you don't even worry about it. But if you are asked to find the range of an even function, you're going to have to find that maximum or minimum value. Any questions? Feeling okay about this so far? Okay, so got a little bit of homework. There isn't a lot. This is kind of just, it's a lot of information, but you see how none of it is really challenging right now? It's still kind of nice and straightforward and generalizing. The next lesson is where we get started with some interesting stuff. So that's why I asked you guys, did you guys like having the information where you were able to take a break from it, go home, do a little bit of homework, come back and have me to answer any questions? Because the next section, which is the remainder theorem, can get a little dicey for students. And I actually wouldn't mind giving you some of it and letting your brain kind of work on it, and then having a little bit of work when you come back. Like for some concepts, there is some research that says it's good to let you guys have your brains have a break to absorb, and then you kind of revisit it 2 times and ask questions. Can we try that? Are we okay with that? So I would say this is not new, but that generalizing gave you a little bit of a push today, but it wasn't huge. The next lesson is big. We do long division again, ladies and gentlemen. When's the last time you saw long division? Grade 3? Yeah, so that as soon as I say it's got long division, people are like, okay, this is going to be tough. But that's why I want to kind of approach it and then kind of reinforce it after your brain's had a break. So can we start up the next lesson at, how many questions is that? 4, so that's 6 questions. There's A, B, C's, and D's, and then I know. Why don't we say, 20-11? I'll check in and see how you're feeling, maybe 11:45, having a little bit of a break somewhere in there. So I just want to try this. You guys seem to be an awesome class, so I can kind of try some things and give me honest feedback. Is it working for you? Is it not working for you? But there's the homework, and we will start again in 25 minutes.